Hello and welcome to my talk about voice-controlled hands-free locomotion for virtual reality system. In this work, we kind of want to present you an alternative way for navigating virtual environments without the need of controllers or any external devices or actually physically moving. So the current state of VR locomotion is that usually we need some kind of controller. If it's a VR controller or some different controller, it doesn't matter, but we need some kind of controller, or actually physically moving our body to navigate within the environment. And those are basically divided into three subcategories. Well, there are actually more, but those are the three most common ones, which the first one being selected based approach, where I point somewhere, or I select an area where I want to go, and then I initialize, for example, teleportation, a motion, or for example, a walk there, to get from my point A to point B. The second category would be walking based, where I actually incorporate some kind of movement or physical movement to move my character in the digital world. So I could walk in place, I could have some kind of redirected walking, or could have a real world walking here. The steering based category is basically mostly combined with some kind of controllers. So for example, if I use my joystick and push my joystick forward, my character would smoothly move forward as well. But in some cases, we don't really want to have a controller. We want to have a hands-free locomotion approach. And why do we need this, or why do we want this? Well, in some cases, our hands might actually be occupied with some other tasks. So for example, if I grab an object, my hands are occupied in that moment. And how do I indicate where I want to go? Or if I use some kind of external devices, for example, some kind of haptic device where I don't really have the opportunity to point somewhere or have some buttons to confirm a movement or something. So for those cases, for example, hands-free locomotion comes in very handy. Or for areas where we don't have controllers, because we're working in a clinical environment where we have some kind of sterile conditions, where we don't want controllers to be included into our digital environment, in our physical world, to control our digital environment. And with all those in mind, we kind of want to create an alternative way of navigation. It doesn't have to be exclusively used, but it could be combined with other approaches, or used as a standalone approach. And for this, we chose voice as interaction method, or as our baseline for our locomotion methods. Voice is actually only sparely researched in the topic of locomotion, but has a huge potential to actually create environments or create locomotion techniques that are quite well received from our participants. And our speech model or our speech approach is basically divided into two phases. The first one is we have to record the voice. We have to process it. So we have a speech recognition path where we use the CalD speech tool that records the voice and actually puts them into tokens. And those tokens can then be semantically passed. By parsing those tokens, we can, for example, look for tokens like teleportation. So if I say teleport me to some location, I could just apply those to our teleport function. And this brings me to the three methods we developed and evaluated within our study. And they can be subdivided into methods that require landmarks and some that don't. So for example, the landmark approach is if we have some environmentally rich scene where we have a lot of objects, we have furniture, we have trees, and with just a lot going on in the scene. So I can just articulate where I want to go. I could say, okay, teleport me to the mirror. And then the speech recognition would recognize teleportation and mirror and would teleport me to that location. But some environments don't tend to have too many of those landmarks. So what do we do then? Well, we could incorporate one of the steering approach, where we use our voice to give our character a direction. So I could say move forward, and my character would slowly move forward. Or I could say faster, I could say faster or slower, I could say move left, stop, and with that I can navigate environments that don't have landmarks. And the third approach is, if we don't have landmarks, we could just generate some. So, for example, on the image on the right here, we have generated landmarks on the floor. We have created a grid structure that is overlaid on top of our floor. So we can subdivide that in as many as we want. We could do 3, 4, 5, 6, or how many we need. In our case, we wanted to keep it simple, and we have as few landmarks as we require. And here in this case, if I want to teleport to the end of the corridor, for example, I could just say teleport me to the 32, and this would bring me to that location. To evaluate those, we performed a user study incorporating actually 4 different techniques. The 3 I just presented you before, and one additional one that has already been proven useful in different studies for hands-free locomotion. And this one is lean to walk, so I would just lean forward to move forward, I would lean backwards to move backwards, and would stand up straight to stop. This approach is basically our comparison point, which is a technique that has already been shown some useful application in the hands-free locomotion domain. And in our study, we performed a very simple maze, which is basically just a predefined path. There are no wrong turns, and the goal was to navigate through those mazes from the start to the end as fast as possible. We performed each locomotion technique twice, and we took care that the order in which those are presented differed between participants, so we have a counterbalance order to not have too many learning effects. So let's dive into our results real quick. We looked at the time to target, or how fast our participant actually performed the study, and there were no hugely significant differences between techniques. We found that some were a little faster, but in general there was no significant difference to show. We found that in the second trial, most of the participants performed faster than the first one, so they actually learned a little bit, and we think that it would still be a little bit faster if we perform them even more. But in VR environment, it's not only important that we have quick results, we should also have results that let the user with a the user would have a good experience, so they don't have motion sickness and they still enjoy using the technique. So we performed 4 different questionnaires that were focused on sickness, comfort, present, and usability. And we found that, for example, in the sickness area, actually the lean to move approach, so where I would lean forward, would actually create a little bit more motion sickness than the voice controlled ones, which is quite good. So we could say that our techniques, our voice control techniques, do not incorporate any motion sickness in our case. The comfort was mostly on the same level, but we found that actually the leaning approach was a little bit more responsive. As the voice-based approaches, we needed to process the voice, and this took about half a second, and so it was not as responsive as just leaning forward. But that's something we would fix in a future work by just incorporating a faster speech recognition model and pass them in a more efficient way. For the presence, we don't have any huge differences, so we could say that our speech-based approach still has a high immersion value for our virtual environment, so we don't reduce any immersion here. For the usability, we also only have minor differences. We found that some participants told us that they would use the landmark and the steering approach more often if they had to in the future. For our conclusion, and to quickly sum up what we did, we present the speech-based, we presented a speech-based hand-free locomotion model that can be generally used as an alternative to navigate within virtual environments, that could also be used when no controllers are available. So it's not only that we can mix and match it, we could also use it as standalone locomotion technique. The performance was pretty similar to one hands-free method that we evaluated it against, and we could also find that the results in usability, immersion, sickness scores are very similar to the other hands-free technique. In the future, we are quite interested in how we can generate those landmarks dynamically. So we showed you the approach where we just created a grid, and we want to go a little bit deeper down that road and see, okay, what works, what is a good approach to dynamically generate those grids, what is a good number, and how can we increase speech-based locomotion within an environment that does not have as many landmarks. Thank you for your attention.